Hey everyone, I hope your day's going well. Welcome to our next video. We're going to be going over 5.4 for this one. 5.4 is vectors. And so at first I'm just going to kind of give you some like definitions and stuff like that. So to start off, we have something called a scalar. So the word scalar it means a quantity that only involves magnitude, no direction. Some examples of scalar uh, quantities would be like length, area, temperature, or distance. These are quantities that are always positive. They only have magnitude. They have no direction. And then we have a vector. And so this is a quantity with both magnitude and direction. So some examples of this would be like force is a vector, velocity is a vector. A lot of times you're going to care whether it's positive or negative. Like it being positive or negative would mean something. Whereas like with a scalar, it's just always positive. And so we'll be talking about vectors a lot. And so with a vector, let me write this out for you. Vector AB, which we basically write as like a ray, has an initial point A and a terminal point B. So this is a directed line segment, so it's a ray. Sometimes they'll write the letters just in bold, like they'll write AB in bold, and that'll mean like a vector. And now, since the direction of a vector does matter, we have to be careful about what we put first and what we put second. So, like letters wise. So, since A is the initial point, we want to put that first. So, that'll be important for us. A little bit of notation here. The magnitude of a vector AB would be written like this. So you basically put it as like absolute value bars, and that would mean the magnitude. And we'll talk a little further about what magnitude will mean. So I'm going to draw something for us. So let's say we have, like, this is our x-axis, this is our y-axis, and we have some vector going through, let's put it right here. And we'll go ahead and say that this is point A, and I'll go ahead and say that this is point B, just to give you an idea of how that like AB connects to actually drawing it in the coordinate plane. So we're going to find that there's some different ways that we can talk about a vector. One of the ways we can talk about a vector is by its x and y components. So just like with angles, you can make them into kind of like a triangle, and you can talk about how big their x is and how big their y is. We can do that with vectors as well. So we call this Vx and we call this Vy. These are horizontal and vertical components. So I'm going to write that for us. Vy is the vertical component. Vx is your horizontal component. And so I'll write some more stuff for you in a second, but right now I'm just kind of introducing some different things. Another way that we can talk about our vector is based on its angle, which we will call a direction angle. And the resultant, which a lot of times we'll just call that r, or you could also call this the magnitude. And that is basically going to measure how long this is. So r, a lot of times we're going to refer to it as the magnitude. And so these two ways that we can talk about a vector, I'm going to write out some forms for you. So we have something called component form. It almost looks like a point, but it's like these little like V, sideways V brackets, and it's Vx comma Vy. So it's very similar to just writing like an XY point, but now it's a vector. So we call it Vx and Vy. So this is not much different from me just saying, like if you look at, if you go back to say 1.4 or 1.5, I can't fully remember where it was, but there was a question that said something like, um, we have this angle going through the point like 2, -1. And I gave you that point, and that told you where the angle needed to be. We can do the same thing with a vector. It's just we call that component form. And then the other way to talk about an angle is to just use r and theta. So I do want to write this out for you. The magnitude of a vector v, I'll just call it v, is equal to the absolute value of v, which we often call r. But you can kind of see it in different ways, so I just want to be specific about that, that sometimes it'll just write out like, here's the magnitude. And then let's give you some very common formulas that you've actually already worked with. So I want to remind you that cosine of an angle is equal to, again, I can't remember if it was 1.4 or 1.5. I think it was 1.4. I said it was x over r. Well, now we're just going to call it Vx over R. So the only thing that has changed is because we're doing a vector, we're going to change it to Vx instead of just writing x. I can change this equation a little bit and multiply both sides by r, and it'll give me that Vx is equal to r times cosine of theta. Another very common equation we'll use is the fact that sine of theta would be equal to y over r, or Vy over r, and that can be rewritten as Vy equals r times sine theta. Magnitude of a vector, just think about what r is equal to everywhere else. So everywhere else that we've worked with, I bet if you go back and look back through your notes, you can find an r equals equation. And it would say r is equal to square root x squared plus y squared. Well, instead of that, we're going to call it Vx and Vy. I'm only going to put these in parentheses so that you understand that it's one value itself. If it confuses you too much to write it as like Vx, Vy, you can just keep writing it as x and y. I mean, we change the language a little bit because it's a vector, but it doesn't actually change any of the work that we're going to be doing. Now, if we're looking for theta, we may want to use some different things. So if I use the equations that I have over to the left, I can say that theta is equal to cosine inverse of Vx over r. I can say that theta is equal to sine inverse Vy over r. I can also use the tangent definition, which like before it was tangent is x over y. I'm sorry, I said that backwards. Sorry, y over x. So it'd be Vy over Vx. Now with theta, I do want to put a note here. It depends on the quadrant, which one we may want to use. So here's really what I want you to take from this. There's two ways to talk about a vector. Either you have to have the Vx and the Vy, or you can have the r and the theta. Those are your options. Like that's what goes together. And then when it comes to having equations for each, so maybe if you know r and theta and you're like looking for Vx or Vy, we can use those equations. Or maybe sometimes we'll want r and theta and we'll know Vx and Vy, so that'll be the other side. So we'll do some different examples. Let's start off with example 1, and I'll just say find the horizontal and vertical components for a vector v with magnitude 8.3 and direction angle 121.3 degrees. Now on the test, I would usually make a note here to round to the nearest tenth. And your homework does this as well. So a lot of times if they want a decimal answer, they're going to tell you how to round. If they want an exact answer, they say something like, leave your answer in terms of roots or a fraction or something like that. I try to do that as well on test 3. Basically, if it says you're going to need to round, then you're welcome to use the calculator. If it says leave your answer exact, you shouldn't use a calculator for that question. So first I'm going to write out what it's giving me and what I want to find. So my magnitude is 8.3. That's going to give me R. So it says my R is 8.3. Then it says my direction angle is 121.3. So that's going to be theta. I also like to draw out like a little sketch of what's going on. So my theta being 121.3, that's going to put me in quadrant 2. And my R is 8.3, which is almost kind of working as like a hypotenuse. So that's how my angle is going. Remember, it always starts at 0. And then the length of this is what is 8.3. And so then what I am looking for is I want Vx and Vy. So I have my R, I have my theta, but I need to find my x and my y. So my horizontal is Vx and my vertical is Vy. So I'm going to use the formulas that we had earlier. So Vx is equal to R cosine theta. Vy is equal to R sine theta. And now I'm just plugging in. So I have 8.3 times cosine 121.3 degrees. Over here I'll have 8.3 times sine 121.3 degrees. Now my x, I get negative 4.3. My y, I get positive 7.1. And all it did was ask for the components, so I'm just going to box them in as they are. Now be careful here. Sometimes I saw some problems that ask for the magnitude of these values. If they ask for the magnitude of the horizontal and vertical components, they're looking for the absolute value of Vx and the absolute value of Vy. So all you will have to do is take the absolute value of both of these numbers. So we're just getting rid of the negative. if we have a negative. But these are asking for different things, so be very careful. If it just asks for the horizontal and vertical component, you will want to keep any negatives that you get. But if it asks for the magnitude of horizontal and vertical, then you're just going to take the positive versions of it. It's because magnitude is a scalar value. It's always positive because it's just about like size. Like we just want to know how big is the Vx, how big is the Vy. We don't actually care about the direction that it's going. But usually with horizontal and vertical components, we do want to care about the direction. So that's why we want to keep negatives, usually, unless it asks for the magnitude of it. So a little bit of something to be careful about. Also, it should make sense for us to have a negative x and a positive y because we are in quadrant 2. So that should make sense. Moving on to another one. Yeah, let's do this one next. This one says find the component form of vector v with a magnitude 40 miles per hour and direction angle 330 degrees. And this one I'm going to make a note for us to leave our answer exact. This means no decimals. So again, I'm going to write out what we're given. So we're being given a magnitude of 40. So that's my R. Direction angle of 330. So that's my theta. And I do like to draw it out. So this is going to put us in quadrant 4 for this one. Now be careful here. When you're looking for component form, that means we're going to be looking for Vx comma Vy. And it's like with these little bracket looking thingies. So let me just find my Vx and Vy first. So I'm using the same formulas that I used before. These are also basically the same formulas that we used in 1.4. So really this section should actually feel kind of repetitive to you. All right, so cosine of 330 degrees, that has a reference of 30 degrees because that's how far it is from the x-axis. And cosine of 30 is square root 3 over 2. And it's positive because it's in quadrant 4. Oop, there we go. This tells me that my Vx is, the 40 can divide the 2, so I would get 20 square root 3. Next, I'm going to get my Vy. Again, my reference is 30. Sine of 30 is going to be 1 over 2. Be careful though, we're in quadrant 4. Sine is negative there. So my Vy is going to give me negative 20. But I'm not done because I need to actually write it in the component form. So that's going to be 20 root 3, comma, negative 20. Now let's do some where we have to find r and where we have to find theta. Let me think. Find the magnitude and direction angle, or sometimes I call it directional angle. It doesn't really matter. Direction angle of vector v, and I'll write the vector in component form. I want to actually pick one that you don't need to use a calculator for it. So let me go ahead and think of this real quick. Let's do negative 1 over 2, comma, square root 3 over 2. So I'm looking for magnitude, so that means I'm looking for r, and I'm looking for the direction angle, so that means I'm looking for theta. I've been given component form, which means I've been given Vx and Vy. So I still would like to draw this, at least to get an idea of what quadrant I should be in. A negative x and a positive y is going to put me in quadrant 2. What that's going to mean is that when I find my theta, theta needs to be in quadrant 2. So I'm going to put a little note here. So first let's go ahead and get my r. So r is square root vx squared plus vy squared. Just the same pretty much Pythagorean theorem that we've always done. So I'm going to have negative 1 over 2 squared plus square root 3 over 2 squared. And then I'll take the square root. So let's see, it's going to give me 1 over 4 plus 3 over 4, which is going to give me square root 4 over 4, which is square root of 1, which is just 1. So here I get that r is equal to 1. Now when it comes to solving for theta, you can use a few different methods. I do want to exercise caution when finding theta because based on the quadrant you are in, there may be a better alternative if you have to use a calculator. Now, you don't need to use a calculator with this one, so it really isn't going to matter if you decide to try to use sine, cosine, or tangent, or whatever to try to find theta. These are actually a little easier if you don't use a calculator. They can get a little harder if you do have to use one. And I will do one like that and like show you what I mean. So I have a few different equations that involve theta. I have one that says Vx equals r cosine theta, and I can solve that for theta. And so in this case, it would be cosine of theta is equal to my Vx, which is negative 1 over 2, over 1. So I'm looking for the theta that makes cosine equal to negative 1 over 2. Now, I am careful here. Technically, if I was asking this in like chapter 4 and this was like an equation that we were solving, I would want to have like multiple thetas. But I know that I'm only looking in quadrant 2. So I'm just looking for the cosine, for the angle theta that would make cosine negative 1 over 2, and it's in quadrant 2. The reference angle that would do this is 60 degrees. So if I come over here, I'm looking for the angle in quadrant 2 with a reference of 60. So I would do 180 minus 60, which would give me 120. So this tells me that theta is equal to 120 degrees. Now the cool thing about this one is that we could have done this in the calculator. You could have typed in cosine inverse negative 1 over 2. If you had done that, it would have just given you the answer of 120 degrees. But you have to be so careful when using the inverse and trying to use the calculator. The reason is because I don't know how much you remember from 4.1, but inverse trig functions can only give you answers in certain quadrants. So cosine inverse can only give you an answer in quadrant 1 or quadrant 2. So if we're looking for answers outside of that, like maybe quadrant 3 or quadrant 4, we would not want to use cosine to help us. For instance, I'll show you this as well. We could have used sine to help us here. And it's not that bad if you do it by hand, but I'm trying to show you if you had used the calculator for this, it would have told you that theta is 60 degrees. The issue with that is it's because you would have, if you use sine inverse only gives answers in 1 and 4 quadrants. So you really just have to be careful. I'll give you some advice at the end on what I recommend doing. But I'm wondering if you have any questions. Oh, so I mean, you can't ask me right now, but maybe write some down if you have any. I'm thinking that I'm like talking to y'all and I'm not. I'm going crazy. I'm just kidding. I mean, I know y'all probably have questions about this because I usually get questions about it. All right. Also, I will say this as well. Sometimes I'll see students do kind of what I just did over here, and they'll go ahead and like box in both of these answers. Please don't do that. There should only be one theta. I don't really know what the point is there. If you're using two different trig functions to find it, you should be getting the same answer. If not, then one of them is wrong. So there's only one theta that you should be getting. Let's go ahead and do another problem. And I think I might have to do some more of those. So let's do one where you have to use a calculator though. So this says find magnitude and direction angle of vector v -2, -5 is the component form here. So again, we're looking for r and theta. We're being given Vx and Vy. So I'm going to go ahead and just do a quick little sketch. Really, I just care about like what quadrant it's in. So this is going to be in quadrant 3 since I have a -x and -y. So that tells me that my theta needs to be in quadrant 3. Oh, let me write down the rounding directions for this. I'll say leave the r exact. I'll say round theta nearest 10th. R we're finding the exact same way every time. So it's square root Vx squared plus Vy squared. Just Pythagorean theorem. So -2 squared plus -5 squared. This gives me 4 plus 25, which gives me square root of 29. So that's my r. And I'll just go ahead and leave it like that. There's really no reason to try to round that. Exact answers are always better. Now for this one, our theta needs to be in quadrant 3. Here's the issue. There isn't a single trig function, inverse function, that can give me an answer right away in quadrant 3. There's none. Cosine can only give me 1 and 2. Sine can only give me 1 and 4. Tangent can only give me 1 and 4. Now, because I've done a lot of these, I do know which one is easiest to use. And in my opinion, that's going to be tangent. I think tangent is easiest to use. And I'll kind of show you why as well. So remember that tangent of theta is equal to Vy over Vx. That means that if I want to use the inverse function, it'd be tangent inverse Vy over Vx. I'm going to plug this in. And see what it gives me. We should think about what we expect. So that -5 and -2, the negatives are going to cancel. Tangent, if it's a positive in the parentheses, it should give me an answer in quadrant 1. And it gives me 68.2 degrees. But be careful, that is not the correct answer because that's in quadrant 1. So that just gave me this angle. Well, if I just want the exact opposite side to that, I can just add 180. Also, you can think of it this way, since this x-axis is 180, I'm almost treating it like a reference angle. And I'm saying, okay, well, what has the reference of 68.2, meaning it's that far from the x-axis, but it's after 180, so add it to 180. So here I'm going to add 180 degrees, and this tells me that theta is actually 248.2 degrees. And that's my correct theta. Now I want to show you what we also could have done, like if we had used a different trig function to find theta. So you don't have to like write this down or anything. Maybe you can just watch and see like which one you think is easier. So my other options for theta, I could have used cosine theta is equal to Vx over r. This would have been theta equals cosine inverse Vx over r. I'm just plugging it in. So this one, because it's a negative, it's going to give me an answer in quadrant 2. That can be kind of hard to then move into quadrant 3. So this one actually tells me it's 111.8. But that's not right. What's really happening there is it's telling me this angle right here, which is 68.2 from 180. So you would have to then find that and then add it to 180. I feel like that's kind of hard to remember to do that, but that's what's happening. You could have also used sine for this one. That one's not too bad to work with. Oh, meant to put a y there. There we go. So this one would have given you -5 over root 29. This one would have given you an angle in quadrant 4. The answer it would have given is actually -68.2. So again, this one would have given you an angle in quadrant 4, and you would have had to like fix the fact that it's in the wrong quadrant. You can decide whatever you think is easier. I personally think that using tangent for quadrant 3 is easier, and then I just add 180. I also like using tangent because if the angle is supposed to be in quadrant 1, tangent can give me that. If it's supposed to be in quadrant 4, tangent can give me that. If it's in quadrant 3, I know I'll just add 180. And then if it's in quadrant 2 is the only time that I personally use cosine. So let me kind of write that down for you. So I personally would not use these for this problem. If I'm in quadrant 3, I would do it this way. But that is kind of up to you. So I'm just going to kind of tell you my advice for these. So when looking for theta, here's my advice. And you can take this however you want. You know, you can do it differently. But if I'm in quadrant 1, I'm going to use tangent inverse. If I'm in quadrant 2, I'm going to use cosine inverse because that's the only one that can give me an answer in quadrant 2. If I'm in quadrant 3, I'm going to use tangent inverse. And then I'm just going to add 180 to it, or pi if you are in radians. If I'm in quadrant 4, I wrote those as thetas, but too many of the same like shape. There we go. I would also just use tangent inverse. So that's really my advice. I would use tangent for everything but quadrant 2. But of course, whatever you get comfortable with is okay. Next, let's look at some operations with vectors. So changing gear a little bit. So if we have a vector A, and I'm going to call that AX comma AY, just because like it has an X and it has a Y. And let's say we have a B vector, and let's call that one BX comma BY. And K is a scalar. Then the following will be true. 1. If you multiply a scalar K by a vector, let's say A in this case, your answer, you'll just multiply the K by each part of the vector. This is actually called the scalar product. Then if we add two vectors together, so if we want to maybe like add A and B together, what you would do there is you would add the X components and add the Y components. So you would do AX plus BX, comma, AY plus BY. And this we call the vector sum. If you want to subtract two vectors, you'll just subtract their components. This is called vector difference. And the last like situation that we will see here is if you want to multiply two vectors. Oh, nope. You would multiply the X components, multiply the Y components. Let me go ahead and use capital letters here. I don't know why I didn't for a second. Let me write this properly. There we go. So you'll multiply the X components, you'll multiply the Y components, and you'll add those together. This is called the dot product. You'll notice that 1 through 3 are the only ones that are actually left as a vector. Number 4, the answer becomes a scalar. So let me go ahead and do an example of like actually using these. So this will be example, I don't actually know what number we're on, 5. There we go. So this one I'm saying let W be the vector -3, 2, and Z is the vector 5, -1. And we'll just say perform the operations. For part A, we're going to do W minus Z. For part B, oh, no, there we go, sorry. We're going to do -8Z. For part C, we'll do 3W plus 4Z. And we'll kind of just work with that for now. I do have a part D that I want to do. I want to do a dot product one, but we'll go ahead and work with these first. So for W minus Z, I would have -3, 2 minus 5, -1. So if I want to subtract these vectors from each other, I'll just subtract the x's, comma, subtract the y's. And that's it. So this one's going to give me -8, 3. For part B, -8 times z, you'll just take the -8 and multiply it by everything in z, almost kind of like distributing. So here I would get -40, 8. So hopefully those aren't too bad for you. With part C, we can kind of do it in pieces. So 3W, so I would do 3 times the W matrix, not matrix. I said the wrong thing. Vector. I don't know why I said matrix. A matrix is a bunch of vectors together. Not what I meant to say though. There is a matrix on my whiteboard in here. Maybe that's why I thought it. Probably not. I think I just said the wrong thing. All right, so let's go ahead and do this one. So -9, 6. And then 4z is 4 times the z matrix, which is 5, -1. Did I just say matrix again? Oh my goodness. I'm just going to blame it on the temperature. So when I'm recording these videos, y'all know that my office was like messed up, got water damage, whatever. The temporary office that I'm in, oh my gosh, it's 75 degrees in here. That is so hot to me. I keep my house at like 68. So maybe I'm going loopy. This has just been a long video though. All right, I'm going to do my best to get back on track and stop saying the wrong stuff. Stop saying the wrong words for things. I meant to say vector, not matrix. Okay, so I did 3W, I did 4Z. Now let me go ahead and add these together. So I'm just going to add these. So I'm going to add the -9 and the 20. That's going to give me 11. And then I'll add the 6 and the -4, and that's going to give me 2. So there we go, that's it. And then part D, I want to do a dot product one. So this one is W times Z. So see if we like multiply two matrices. So W was negative 3, 2 times Z, which is 5, negative 1. So be careful here. When you multiply these, you multiply the x's together. So negative 3 times 5. And then you multiply the y's together. So that's 2 and negative 1. And then you add them together. That's what people usually miss for this question. So I'm going to get negative 15 plus negative 2, so negative 17. So that's really important here. You have to add those numbers together. A lot of times people will write it as like negative 15 comma negative 2 and then they just leave it. Like they write it as like a new vector, but that is incorrect. Make sure you add them together. Okay. So this can be kind of interesting for us. This is something you'll probably talk a little bit more about in an actual like physics class, but it says if A and B are not parallel and they have the same initial point, then I'm going to show you like what this looks like on a graph. So if we have like A here, and then we have B here, so they have to have the same initial point. So they're starting at the same place. A minus B would form a triangle. And that can actually be used for different things. Um, Later in 5.5, we're going to do some airplane problems. And we're going to make them as triangles and like we're going to use different ways to solve triangles to figure them out because we're a trig class. If we were more of a physics class, I would actually probably use this to try to solve that. Like I would use component forms and stuff and I would just subtract the component forms. And some people say that that's easier, but that's more of like the physics approach to it. And here I try to use more like the law of cosines, law of sines, and stuff like that when it comes to working with triangles. So we'll probably use that. But another way to solve those problems, just for later when we get there, technically you could use the component forms. You do have to be a little careful with signs, though, like negatives, positives, and stuff. But if we want to find the angle between these two vectors, this angle right inside of here, we actually have a formula for that, and it comes from law of cosines. But I'm just going to give you the easier formula. So here you go. It says if A and B are non-zero vectors and theta is the smallest positive angle between them, Then we have this formula that says cosine of theta is equal to the dot product divided by the magnitude of A times the magnitude of B. So I want to remind you here that magnitude of A so hence we're going to be finding like R when we look for that. And so this formula actually comes from law of cosines. But you can just use the easier version. The whole smallest positive between them part of it is really just so that you know like that we're finding this angle inside of here and not like this angle outside. So it's just saying like we're looking for the smaller angle, not the one like around the two vectors. So of course we'll do an example. I think we're on example 6. So this one says find the smallest positive angle between the vectors. And we'll do 2 of these. Part A, we'll do -3, 2 and 4, 5. And then part B, we'll do -5, 9 and 9, 5. So I'm going to use the formula. So it says cosine of theta is equal to the dot product of the two divided by the magnitude of the two. There we go. So I'm going to do mine in pieces. So first let me find the dot product. And we'll call this one A and we'll call this one B. So for A times B, remember I would multiply the x's. You should take a minute and do this. Like you should definitely try this on your own. Plus, multiply the y's. So this gives me -12 plus 10, so -2. Then I'll find the magnitude of A. Now remember, magnitude is when you're finding R of a matrix, so we're basically being given like our Vx and our Vy, and we're looking for the R. So that's going to be the square root, -3 squared plus 2 squared. So square root 9 plus 4, so that's square root 13. Magnitude of B, I'm going to do the same thing. So I've got 4 squared plus 5 squared. So this one is 16 plus 25, which is 41. Now I'm going to plug everything back into the formula. So I get cosine of theta is equal to -2 over root 13 times root 41. Now I want the theta, so I'm going to have to use the cosine inverse. Be careful here. I usually see a big mistake here with the calculator. make sure you keep that denominator in its own parentheses. So put one like around this, like before you put in your square root. And the answer you should get for this one is 94.97. If you get any kind of error, I am very sure that it's a parentheses error. You're welcome to let me know, and I can always jump on a call with you and look at how you're plugging it in and let you know. So that one's done. Now if we do part B, so again, I'm going to use the same formula. First, I got to take the dot product. So I'm going to do that. So I have -5 times 9 plus 9 times 5. So this is going to give me 0. Interesting. Think about this for a second. Will it matter if we find our denominator now? Because now when I plug it into the formula, I have 0 over stuff. 0 divided by anything is just 0. So I'm just going to get rid of that and just say cosine theta equals 0. So this one, I did not have to find the denominator because it would have just gone away. But if you finish solving this one, cosine inverse of 0 is 90 degrees. So this one actually just shows us something cool. If the dot product equals 0, then the vectors are perpendicular. So the smallest angle between them is 90 degrees. That means that they're perpendicular. Okay, moving on. Next up is unit vectors. Talking about unit vectors. Let me write that a little nicer for you. There we go. Unit vectors. What we're going to find here is another way to write our vectors. So I'm going to write out some definition type stuff for you. So let me write that first. I is the vector 1, 0. This is not I as in like imaginary I. This is a different I. This is like vector notation I. And J is the vector 0, 1. These are called unit vectors because they have magnitude 1. Any vector, let me write like ax comma ay can be written as ax comma ay is equal to ax times 1, 0 plus ay times 0, 1, which would equal ax times I plus ay times j, called a linear combination of unit vectors. Okay, that is a super mathy definition, and I will give you a second to just kind of take it in. I think you should pause and maybe just read it, try to make sense of it yourself. Really, I want you to know that it is way less complicated than you probably think it is. It's really just another form of writing a vector. So instead of writing it like with the brackets and the comma as like component form, we can write it as AXI plus AYJ. So let me show you with an example, like literally just how to rewrite vectors. So this is example, I don't even know, okay, 7. So we'll say, write each vector as a linear combination of unit vectors. I think what really throws people off is linear combination because it sounds crazy. But really, linear just means x and y. And then a combination of the two, you're just like adding them together. So you're basically taking your vx and your vy and you're writing them in a different way where you add them together instead of putting a comma. So for the first one, I'm going to give you this vector a equals, and I'm going to give you the component form, -2, 6. And then for b, I'm going to give you the vector -4, -1. And now it may have been better earlier, like maybe it would have made a little bit more sense to you if instead of using A, I had used V instead. If that's the case, I can write it like that. So if it was like a Vx comma a Vy, really what you're going to turn this into is Vx times I plus Vy times j. So just a new way of writing the vector. So here we're being given Vx and Vy. So it's going to be -2I plus 6j. And that's it. So it's just instead of using the brackets and the comma, you're writing it in a different way with I and j. For part B, so this is my Vx, this is my Vy. So I'm writing it as my Vx times I, so -4 times I, plus my Vy times j. Now this one you can write a little nicer and just say -4I minus j. And that's it. Now I want to show you one more question of this type, kind of bringing it back to what we did earlier, where maybe like we're given r and theta. So let me say, give you like a longer example. So write vector V with a magnitude of 8 and a direction angle of 225 as a linear combination of unit vectors. So go ahead and pause, write it down, take in what it's asking. We're being given the magnitude, so that means we're being given our R. We're being given our direction angle, which means we're being given theta. We're being asked to write as a linear combination of unit vectors. So that's going to be Vx times I plus Vy times J. So the only difference between this one and the example we did earlier, I can't remember what number it was, but hopefully you can find the one I'm talking about, where I gave you R and theta, but I asked for like component form. The only difference is how we're going to write it at the end. Everything else is roughly the same. I would still want to plot it, so it looks like it should be in quadrant 4. I know because that's where 225 is. I'm still using the same equations for Vx and Vy. So I'll plug those in. Cosine of 225, this has a reference of 45, but it's in quadrant 3, so it'll have to be negative root 2 over 2. Same story, this one's negative root 2 over 2. Now simplifying this would be negative 8 root 2 over 2, which simplifies to negative 4 root 2. So for my final answer here, I need to write it in the form. So negative 4 root 2I minus 4 root 2j. And I just put the i's and the j's at the end. Just make sure it doesn't look like it's like in the square root or something. Some advice that I would give you when you're looking for Vx and Vy, make sure you always check those signs. I can be kind of bad about it. I'm a little nervous that I missed one earlier in this lecture. So just be careful with those negatives and stuff, like what quadrant and all that you're in. But that's going to be it for this section. If you have any questions, please feel free to reach out to me. And otherwise, I hope you have a wonderful day. See you in the next video. Bye-bye.